All right, so welcome back to OneClass. If you're tuning in for the first time and you don't know what we're about, OneClass is kind of it's basically an online resource where we are creating these live streams and videos for you to kind of follow along, and they're all posted here on youtube.com/oneclass. And what we're doing here is we're providing and we're verifying solutions to frequently asked questions in the secondary level and the university and college level in both mathematics and in chemistry. So that's kind of our situation here, and we're basically our goal here is, despite the COVID-19 school closures, we're aiming to provide the best possible online resource for students kind of moving forward, despite school being closed down. So we're providing these videos, and we're creating these videos basically 7 days a week, and we're streaming our lessons online, so you could access them at any point in time. So today what we're going to do is I have 10 questions for you, and we're going to look at probably the senior level chemistry courses, and specifically in grade 12 chemistry. And what we're going to do is we're going to answer these 10 problems, and we're going to verify these solutions together. So my name is Joey. I'm currently a secondary school educator in the Ontario. So what we're doing here is that my teachable subjects are chemistry and mathematics and in music as well. So I'm hopefully going to be helping you, walking you through these questions, and I will help basically any questions that you have. So if you're in the chat, you can feel free to say hi, and you can kind of follow along, and we can work through these problems together. So without further ado, let's get started on these 10 problems for today. So first question is asking which is not polar, and we have basically 4 compounds here. So I have number 1 here. It says I'm going to say which is not polar, and then I'm going to write out the chemical formulas for you. So I have, this is CH2F2. I have CH3COCH3. I have SiCH34, and finally CH3NCO. So let me draw the chemical compounds for these guys here. So which of these are not polar? So when we talk about polarity, we're talking about the difference in terms of electronegativity between 2 atoms here. So the first one here, I'm going to label this A here. So A here is CH2F2, right? So if I'm going to have the carbon in the middle, carbon is going to be in the middle here. It's going to be bonded to 2 hydrogens here, and also bonded to 2 fluorines here, right? So in this case here, I'm going to have I do have it is polar, right? In this case, the fluorine here draws out electronegativity. This is partial negative here, and carbon makes it partial positive here. So it basically, I have electron, it's drawing away electron density from the molecule here. So fluorine is pushing, it's attracting, has a negative charge, whereas carbon here would have a slightly more positive charge because of the dipoles that are created here. So in this case, this molecule here is polar. So A is polar, which means this here is not the correct answer. We can look at B here, which is CH3COCH3, right? So I'm going to have this carbon bond here, and it's going to be bonded to an oxygen that's bonded to another CH3. And then I also have CH3 also like this, which means this guy here should be a double bond on the oxygen. So give me a second here. So I would have a double bond oxygen here, and this is bond CH3 like so. So this here is going to be my chemical structure for this guy here. And here we also have a dipole, right? We have a dipole between, again, the carbon here is partial positive here, and the lone pairs on oxygen will make it partial negative, right? These lone pairs here are partial negative. Again, oxygen is pulling electron density away from the carbon here. So this guy here is also polar. So B is not our correct answer. We can look at C here. And C here, I have SiCH34, right? So Si will be our silicon, will be our middle guy here. So we bonded to CH3, 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 and CH3. And let's look at our periodic table here. Let's see where how many bonds silicon make here. And silicon here, it's in group 14, which means it can make 4 bonds here. So again, I have 4 bonds here. It's going to saturate the silicon here. And these carbons are also saturated as well, which means there's no dipole moment here. If you look at the electronegativity between silicon and carbon, there's barely anything, because again, they're in the same group here. So in this case, this guy here is nonpolar. So this here is my non-polar structure because I have everything is saturated. Carbon's bonded to four things here. Silicon's also bonded to four things, which means there's no room for a dipole here. And the difference in electronegativity is very, very small here. So in this case, silicon here will be my correct answer. And I'm going to verify that D here is also not the correct answer for you as well. I'm going to draw CH3NCO, and it says the carbon is double bonded to the nitrogen and oxygen here. So I'm going to have C here. It's going to be double bonded to an oxygen here, and this is bonded to a nitrogen here, and bonded to CH3 like so. I believe this is our compound here. So in this case, this guy here also has it also has a dipole, right? As you can see, carbon, the electronegativity difference between carbon and oxygen, I have a partial negative here and a partial positive here. And then on nitrogen, I also have a partial negative here as well, right? So again, these two things are pulling electron density away from the carbon. Therefore, it is going to be a polar molecule here. So therefore, C here is my correct answer. So polarity is caused by uneven electron density. That's good. CF4 is non-polar because all of the atoms surrounding the carbon are identical. This is not the case with CH2F2, and therefore it has a higher boiling point, but doesn't really describe here our correct answer. So I'm going to say here this is an incorrect solution or incomplete solution. The molecule that is polar would be basically SiCH3,4 because or non-polar because silicon is bonded to 4 different compounds and carbons are also saturated. Therefore it does not allow for a dipole moment. Electronegativity difference between silicon and carbon are small, therefore even electron density, I'll say. So this here is an incomplete solution. The molecule here is, again, silicon. This would be bonded to 4 methane groups. So solution, I'm going to say is incorrect just because it's an incomplete solution here. All right, that's number 1. Let's look at number 2 here. It's asking us which of the following aqueous solutions has the highest boiling point. So it says I'm looking for the highest boiling point here, and it says here A is 0 point and then something WMKCl. D is A and B. Okay, so I think the formatting is weird here. So I'm gonna write this in order here. So it says here 0 point something. It's probably 0.2. I think they tried to write 0.2 KCl. B would be 0.2 molars of this is sodium sulfate. C would be 0.2 molars of this is calcium nitrate. D here is A and B, and E here is B and C. Okay, so it's asking us which of the following aqueous solutions has the highest boiling point here. So when we talk about highest boiling point, we're looking at all of the properties of these guys here, right? So potassium chloride, sodium sulfate, and calcium nitrate, they're all ionic compounds, which means they have very, very high boiling points here. So let me just write this out here. So these are all ionic compounds, which means the only intermolecular forces we have here are the ionic properties here. So we only care about the ionic properties. We don't care about, there's no hydrogen bonding, there's no dipole moments, etc. here. So we only care about the ionic properties here. So therefore, so when we talk about ionic compounds and how it affects boiling point, we talk about how many molecules are actually in the compound here. Because they're all in the same solution, same concentrations here, we can actually ignore this and we can actually just specifically look at the compounds here. So as you can see, potassium chloride here is made up of two atoms, right? It's made up of potassium and chlorine here. So I can say this is made up of two atoms here. Sodium, as you can see, I have two sodium ions, so two here, and then I have a sulfur, and then I have four oxygens here, right? So this here would have, it's a much bigger molecule, you could say, because I have more compounds here. And same with calcium here, I have one calcium, I have two nitrogens, and 6 oxygens here. So in this case, when we talk about boiling points here, I would have to say that potassium chloride would have a lower boiling point than sodium sulfate and calcium nitrate, just simply due to size, right? So as you can see, they also wrote here as well, right? In the given solutions, they have the same concentrations, but number of particles are different, right? And boiling point is elevated by increasing the number of particles here. So as you can see, potassium chloride, as again, has the lowest boiling point, so this would be our wrong answer, which means D would be also wrong here. And sodium sulfate and calcium nitrate, they're very similar in size, right? As you can see, sodium has 3 ions here. You have Na plus and SO4 minus, or you have two Na pluses and one SO4 minus. And for this one here, you have one Ca plus and 2 NO3 minuses, right? So in this case, you have 3 ions here and 3 ions here. Therefore, B and C are both about the same boiling point here. So they have almost the same boiling point, you can say, which means that E is the correct answer. So the solution here is correct based off basically size of the ions and number of ions here. So solution is correct. Good analysis here. Let's look at number 3. Number 3 is asking, consider these two entries from a fictional table of standard reduction potentials. Which pair of species would react under standard conditions? And it gives you these 3 here, or 4 options here. So x2 plus 2e minus would get me x solid. This E here would be 2.22 volts. And then y2 plus 2e minus give me ys. E would be 0.21 volts here. So it's asking which pair of species would react under standard conditions here. So when we look at standard reduction potentials, we're looking at, okay, hydrogen, again, I have my standard reduction potentials here. These are all being reduced, right? I'm gaining electrons in this case. X2 plus gains electrons to form X solid. Y2 plus here is going to gain 2 electrons to form Y solid here. If you remember, recall the hydrogen is our base kind of point here at 0, right? So anything that's above, in terms of above here, it's going to be, these are both positive charges, right? So 0.21 is very, very close to this this guy here, right? It looks like very 0.22 here. So this, you can think of this as like sodium. This is silver chloride. Reduction of silver chloride gives you silver plus the silver solid and the chlorine ion, and 2.22 is all the way up here, right? It's all the way up here in terms of the half reaction. This is very, very electronegative here, because again, F2 plus is very electronegative. This is also very electronegative here. So you can assume that X here would be a halogen, whereas 0.21 is again it's less reactive here. So it's asking us which pair of species would react under standard conditions. So we know that because X2 here has such a great reduction potential, X2 is obviously going to react here, and it's going to probably react with our Y here, right? So again, it says the most positive will reduce here. So again, this is my most positive volts here, so it's going to reduce, which is correct, which is therefore this one here will oxidize. So in this case, we're gonna have this species here, so X2 and Y, which is the correct answer here. So let me just show you. So it means because this value here is greater than this value, this reduction will happen, right? So I'm gonna get this reaction here is going to be my reduction, and if I have a reduction, something needs to be oxidized, right? So so this guy here is going to get oxidized here. So it's gonna be YS is going to form these two guys here. So this one will oxidize. So which reactions will react together? I can basically cross these guys out to form my net ionic equation, which is X2 plus here, sorry, plus ys would give me xs plus y2 plus. So these two guys here are going to be my reactants, or pairs of species that will react. So x2 plus and y here is the correct answer. So solution is correct. Good analysis here. you really just care about the reduction potentials, right? If the higher the reduction potential, obviously the reduction will happen. And if the reduction will happen, then the other one will have to be an oxidation reaction. Solution here is correct. Okay, number 3. Let's look at number 4 here. It's asking, is sodium carbonate acidic or neutral? Why? Show all work here. So, is Na2CO3 acid, base, or neutral? It says why, show all work. So so this student here wrote slightly basic, and this here is I'm gonna walk through their logic to see why it's correct here. So basically, sodium carbonate is an ionic compound, and basically, what it's gonna do, it's going to dissociate, right? It's going to dissociate into these two guys here, and I'll write down the chemical equation here. So Na2 is going to dissociate. Na2CO3 is going to dissociate into my, I have Na2 plus, so my sodium ion here, and this will be my carbonate ion here. Sorry, this is one plus carbonate ion here, and I can balance this chemical equation obviously, and I would get this guy here, right? So this here would be a balanced chemical equation for the ionization reaction of sodium carbonate, and we know that actually with carbonate here, CO3 is actually going to react with water as well, right? So I can say that CO3 minus, when I react it with water, it's going to be in an equilibrium and form basically carbonic acid here. So it's going to form H2CO3 plus OH minus here. So this here makes it a weak base, right? Because this here forms, again, I form here an H2CO3. Actually, no, sorry, this is not carbonic acid here. I believe this is it's just H2CO3 here, but it forms this hydroxide ion, and once it forms this hydroxide ion here, we know that this this acid here, this hydroxide ion is slightly basic, right? We have a weak acid here, and we have a strong base here, so it's going to be slightly basic in terms of this compound here is slightly basic. We know that our carbonate ion is going to react with water. It's going to be in an equilibrium with H2CO3, which is our carbonic acid, again our weak acid in this case. We have a weak acid, and we're gonna have a strong base in our for our conjugate base here. So in this case, if this is our weak acid, if this guy's our weak conjugate acid, this would be our conjugate base, and this here would, this here would be our base, and this here would be our this would be our acid here. This would be our base, and this here would be our base and our acid here. And this would be conjugate base here. So acid and water would behave as acid. The carbonate ion will react as a base, and it will form basically a weak acid and a conjugate base, which is our OH minus here. And this is going to be slightly basic because I have OH minus, which is formed in our solution here. So it's going to be slightly basic. This solution here is correct. It's a great analysis as well. Correct solution and analysis here. Sweet, let's step 4. Number 5, we're looking at calculate the pH of a 1.60 CH3NH3Cl solution. Kb for methylamine is that. So 3.7 times 10 to the negative 4. So this is question 4? Question 5, sorry. So this is I want the pH of 1.60 molars of a CH3NH3Cl solution, and the Kb for methylamine. So Kb for CH3NH2 would be 3.7 times 10 to the negative 4. So basically how we want to form how we want to write this chemical reaction. So we're given this guy first, right? So we want to figure out the dissociation of this guy first. So we have CH3 NH3Cl, right? So this is going to dissociate into two ions. Again, it's going to be my CH3NH3 plus Cl minus, right? It's going to dissociate if you put it in an aqueous solution here. And then finally, this here is now my methylamine, and this here will then react with water, right? CH3 NH3 plus water will be then in equilibrium, and I'm going to get here a CH3 or H3O plus first, and then an NH2, right? CH3NH2 is going to lose a hydrogen here. NH2, it's going to lose a hydrogen here. So this here is my equilibrium reaction, and then the Kb for CH3NH2 would be 3.7 times 10 to the negative 4. So they actually wrote the exact same thing here, which is great. But again, if I look at my kind of compound here, I'm forming H3O plus here, which is an acid here. So this here I would actually have my Ka here. So I have to actually solve for my Ka. So because I'm given a Kb, what I'm going to have to do is relate it to Kw, right? Because I know that Kw equals Ka times Kb. I know that Kw is 1.0 times 10 to the negative 14, which will equal Ka times 3.7 times 10 to the negative 4. We should make Ka would equal, I simply have to divide both sides by 3.7 times 10 to the negative 4, which will give me 2.703 times 10 to the negative 11. This will make Ka for my solution here. And what I can do now is I can write out my my formula, right? I have Ka here. It's going to equal, again, H3O plus, which is what I want to find out, times my CH3 NH2 times, all over, this is CH3 NH3 CH3 NH3 plus, and then all of water here does not participate in my Ka reaction here. I know my pH of this solution here is 1.60, right? So this is actually going to fully dissociate into this ion here, which means I have 1.60 as my concentration here. I don't know these guys here, so what I can do is I can simply just use an ice table to figure out the equilibrium of this guy here. So I have my K expression, which is great. I'm going to have to do an ice table now. So let me draw out the ice table here. So I have, So again, I have CH3, and because I want to figure out my my things to plug into my K, right? So I have CH3 and H3 plus H2O. It's going to give me CH3 and H2 plus H3O plus. So again, ICE, initially I'm going to have, again, I have 1.60 molars of the solution here. I don't care about my water here, and this here I have 0 and 0. I'm going to subtract x, I'm going to add x on both sides here, and I'm going to have this and like so. I can substitute these guys into my K expression here. So let me rewrite the K expression as my variable. So obviously hydronium here is x here, methylamine is also x here, and we divide it by 1.60 times 10 to the negative x, and this will equal my Ka, which is what I solved for initially here, which is 2.703 times 10 to the negative 11. I'm going to approximate it and assume that this is much smaller. This x, I'm going to use a small x approximation here, so I can cross this out. So simply, I'm going to have x squared on the top, and I'm going to multiply both sides by 1.60 here to get 4.32 times 10 to the negative 11. And I'm going to square root both sides to get my x value here. So I'm going to square root this number. I'm going to get 6.576 times 10 to the negative 6 here. And this is going to be my x value here, which is my concentration of both my hydronium and CH3NH2. So this here would also become the concentration of my hydronium ion. I simply now just have to solve for that pH. So I know that pH equals negative log of my hydronium ion. pH is negative log of basically 6.576 times 10 to the negative 6 moles, because this is my concentration of my hydronium. I plug that into the calculator, and I would get a pH of 5.818 here, and this will be my solution for this question here. So 5.18 here is my solution, which is the correct solution that they have here. So the solution is correct. Again, the hydronium ion calculated that correctly as well. So the solution here is correct. Great analysis here. All right, that was number 5. We can look at number 6 here. So number 6 is asking how many bonds can carbon form and why is this important? So carbon can form bonds depending on its electron configuration, right? So I'm gonna write this down here. So carbon can, or let me just write here how many bonds can carbon form and why. So if you look at the electron configuration of carbon here, so carbon here has, if I look at my periodic table, carbon exists here, right? So my first thing I have to write is 1s2 and then 2s2 and then it's 2p2, right? So it's carbon here has electron configuration of, this is 1s2, 2s2 and 2p2, right? Yes, 2p2 here. And what we can do with this information here is what it goes through is basically gonna hybridize, and basically these sp3 sp orbitals here are going to rearrange themselves to create kind of four pockets for electrons to sit on. So basically carbon here is going to hybridize to form basically sp3 orbitals here. So basically I'm going to get, if I were to draw out the energy level diagram here, I have 1s2, so this is filled here, and then I'm going to have 2s2, and then I have 2p2, right? 2p2 here. So initially I had something like this, which means that I can't actually form my bonds here. So what it's going to hybridize. So let me draw this out for you. It's going to go through hybridization. And then I'm going to get, again, I still have 1s2 in the ground state level, but I'm going to have these 2s2 and 2p2 orbitals are going to hybridize to become the same energy level here. So I'm going to get actually four specific orbitals. So I'm combining this 2s2 orbital and the 2p2 orbital to form 2 sp3 orbitals here. So this here, again, my electrons will then split up. I'll have, according to Hund's rule and the off-bound principle, it's going to occupy all the electrons first before it doubles up. So again, here it means that all my electrons here are filled with one. It's half filled. It's gonna be a half filled orbital here, which makes this very, very stable. So this here again, how many bonds can I make then? I can make 1, 2, 3, and 4 bonds. So carbon here can make 4 bonds here, and this is done through hybridization of the 2s2 and the 2p6 orbitals to create sp3 orbitals here. Well, carbon here, again, is the foundation of organic chemistry, right? Carbon here is always bonded. CH3, for example, is bonded to, or CH4, sorry, is bonded to always 4 carbons here. And this kind of starts our backbone of organic chemistry, right? We have alkanes, alkenes, alkynes, and all the functional groups are all based on the fact that carbon can make 4 bonds here. So again, they did the exact same thing. They drew up the electron configuration, and I believe that I don't know if they talked about hybridization. They should have in this case. 2s2 and 2p orbitals are the valence electrons. Carbon has 4 valence electrons, full octet here. So I think they're actually missing this point of hybridization. So let me just say that's incomplete solution. Good analysis for writing down the electron configuration of carbon. However, missing the key point of hybridization. Where the 2s2 and 2p6 orbitals are mixed and forms 2 sp3 orbitals, meaning that carbon is half filled, therefore allowing for 4 bonds on carbon. Sweet. So I'm going to say solution is incorrect because they were just missing some key points of this information. Because if I had this guy here, I can't see that I can make 4 bonds here. I can't be like 1, 2, 3, 4 here. That just doesn't make sense. I need to make hybridization occurs to allow me to make 4 different bonds here. You can think of it as 4 hydrogens with the red arrows here, 4 chlorines, 4 fluorines, whatever you want in that case. So that's 6 here. Let's look at number 7. It says which compound is more acidic, soluble in an acidic solution. I believe I actually already answered this problem before in a previous video, but let me just write this down. I have PBBr, I have Cu, I think that's Cl, C here is AgI, and D here is BAR. What's BAR? Let me just look at the solution here. Barium, BAF here, Okay. So it says here, which compound is more soluble in acidic solutions than in neutral solutions? So we basically have to look at these kind of ions here, and we have to look at kind of the activity series. So if I were to add acid into all of these guys here, will it actually dissociate here? So I have HCl. If I were to add HCl here, would it actually react here? Would I get lead chloride and hydrobromic acid? So in this case, would I get PbCl plus HBr? In this case, this would not actually happen because right now I have this will not actually displace the chlorine here because this will not react because I would not have a double displacement reaction here. Chlorine is more electronegative than bromine here, so it's not going to actually kick this guy out. It won't actually kick this out. So bromine would, the lead here would not be able to kick this hydrogen out. So A here would not be more soluble in an acidic solution. Same with B here. B here is copper chloride. If I added, let's say H2SO4, for example, would it actually go to copper sulfate plus HCl? Again, I probably would not have this again because again I have HCl here, which is a very strong acid here, and I'm already adding a strong acid here. So again, this would not probably be our answer as well. I have AgI here, right? AgI. If I added HCl again, I would get silver chloride plus HI here, and this here again, this here is not as soluble here. As you can see, C here, silver iodide. Iodide is a weak conjugate base, therefore it does not increase in acidic solution here. So it's not very good. And then finally, for D here, if I were to add hydrochloric acid, I would get barium chloride plus HF here. And again, or I would get basically F minus. I would basically this associates into F minus here, and the F minus here is definitely a weak acid. It's a strong conjugate base of a weak acid here, of a strong acid here. So therefore, this actually increases in an acidic solution. So this solution here is correct here. Solution is correct. Good analysis here. Okay, that's number 7. Let's look at number 8 here. 8 is asking what is the electron configuration for a nitride ion. So I have a nitride ion. So let's look at what a nitride ion first is. What is a nitride ion? So a nitride ion here, it lies on this N here, right? It's nitrogen here, but it's an ion, right? So it's going to be N, and then I will have some type of charge here. In this case, it lies on group 15 here, so I'm going to have a charge of 3 minus, right? So this will be N 3 minus. So in order for me to write the electron configuration here, I would have to look at, again, I go down the periodic table. So I go across and go down, right? So if I go across, again, this first line here would be 1s2. So N3 would be 1s2. And then I have these two guys here. This will make a 2s2. And then finally, nitrogen lies here, right? So there's 2, 1, 2, 3, 4, 5, 6, right? So there's 1, 2, and 3. So it'd be 2p3, 3 here, but this one is for my, this guy here is actually for nitrogen by itself. If I had a nitride ion, I have N3 minus, which means I'll have 3 more electrons in this case, which means in this case here, this p orbital will be filled to 2p6 here. So this is for an N3 minus ion. The nitride ion will have a filled 2p6 shell. If I were to again draw the energy level diagram for this guy here, I have 1s2, which is the lowest guy here. And then finally 2s2 would be here, and then 2p6. All of these guys will be filled with electrons here. So this is my energy level diagram plus my electron configuration for my nitride ion. So again, they talked about Aufbau principle, which is good. And I'm just going to skip down to the answer here. So again, this is good. So nitrogen here, they wrote 1s2, 2s2, 2p3, which is the nitrogen ion. However, nitride ion is N3 minus, right? So therefore, it's 1s2, 2s2, and 2p6, like I wrote here. And then I also went the further step and I drew the electron energy level diagram for this guy here as well. So this solution here is correct. Again, nitrogen here, again, it used to be 2p3, but I'm adding 3 more electrons to make it the nitride ion. So it's going to be 2p6. So solution here is correct. Good analysis here. Number 8. So this is number 9. So it's asking us what intermolecular forces are present in ethanol. So ethanol, you can I'm going to draw ethanol as I'm going to draw ethanol a couple of times here. So ethanol, I can say it's this guy here. A line diagram of ethanol is given so, or you can write basically this is CH3 CH2OH, right? Again, I have 3 hydrogens here and 2 hydrogens here, right? H, and H, and H, and H here. So CH3, CH2 would be ethanol here. So if I were to draw, again, a diagram, a condensed structural diagram, it might be able to, help you visualize the intermolecular forces here. So let me draw this out for you. So what do I have? What intermolecular forces are present here? So let's look at the most obvious one, which is the strongest intermolecular force in terms of covalent compounds here. It's going to be my hydrogen bonding, right? So again, this here first, I have hydrogen bonding. It is present in ethanol, right? So hydrogen bonding, again, this H is bonded to this F here. These two guys, again, these two guys here, I have hydrogen bonding, very, very strong hydrogen bonding, because I have, again, hydrogen is bonded to either N, O, or F here. In this case, it's bonded to O. So again, this here is a very, very strong bond in terms of intermolecular forces. It's one of the strongest ones because of the electronegativity difference between hydrogen and oxygen here. So hydrogen bonding exists in ethanol. Number 2, dipole also exists in ethanol here, because I have a partial negative charge on my oxygen here. So this here is pulling electron density away from my carbon, right? Where carbon here, the electronegativity difference between carbon and oxygen is great. So therefore I have a dipole force here as well. So I have 1, 2, which is great. And then finally, my third, last but not least, I have London dispersion forces. And this is the weakest intermolecular force in this compound here. So I have London dispersion forces, but this contributes very, very little in terms of my intermolecular forces. And it's just the weak electrostatic forces that are formed in these the carbon-hydrogen bondings here. So let's see here, solution here. Solution says ethanol is polar covalent, has OH bond. That's good. Hydrogen atom of one ethanol molecule will react with OH bond of another ethanol molecule to form a hydrogen bonding between the molecules. So this here is good. So I have hydrogen bonding with here as well. And I don't think they said dipole or dispersion forces here. So I believe that this solution here is incomplete because they forgot dipole and London dispersion forces. So ethanol contains hydrogen bonding, dipole, and London dispersion forces. So they basically the solution gave us definitions of all intermolecular forces, but missed out on dipole and London dispersion forces in the solution. In the answer, I'll say. So this solution, I'm going to say, is incomplete because they forgot to mention dipole, and London dispersion here. Number 9. So we have 2 more questions here. We're on track to finish on time here. So number 10 is which of the following solids has the highest melting point? So I'm looking at highest. Melting point. And I'm given compounds, so it's CS in the form of a diamond. I have Kr, solid krypton. I have NaCl. I have H2O. Okay, so when we talk about highest melting point, we have to classify these compounds as: are they covalent? Are they ionic? Are they molecular? What are these guys here? So carbon here, as in the form of diamond, is actually a covalent network here. So it's going to be basically it's C bonded C bonded C bonded C, and basically it's basically a bunch of carbons bonded to each other. So this here is a covalent network compound. Krypton here is simply just a it's a noble gas, right? So krypton here exists as a noble gas. So if you look at the periodic table, krypton exists in group 18 here. So it's not really a very it's a stable compound, but krypton's solid here. Solid here makes a big difference here because krypton, again, noble, it's usually in a gas form. However, if it is a solid form, it's a very weak structure here. So it's a noble gas, but solid form is weak because it prefers to exist in a gas form. So the solid is probably going to basically sublime or go through the process of sublimation to form a gas here. So krypton is actually the weakest one here. NaCl is obviously my ionic compound. So I have, it can be dissociated into the sodium ion, cation, and the chlorine anion. And finally, water here is simply a covalent compound, right? So if I were to rank my intermolecular forces here, covalent networks is definitely the strongest one. So diamond, think of a diamond, very hard to melt. Covalent networks are very strong because they rely on each other for them to produce their covalent network here. So diamond will have my strongest, will have my highest melting point. Then it will be my ionic compounds, right? Ionic compounds also are very strong because, again, it's the exchange of electrons. Right? One sodium is giving away its electron, chlorine is accepting its electrons here. It's forming an ionic bond, very strong. Thirdly, we have our covalent compound here. H2O is our third basically highest melting point because of, again, if you draw the structure of water here, you're going to have hydrogen bonding. So hydrogen bonding, again, strongest intermolecular force in a covalent compound. So this would be making number 3. And finally, krypton would be number 4 in terms of melting point because it's in a solid form, so it has very weak van der Waals forces here. So the solution here is correct. Diamond, sodium chloride, water, and then krypton here. So solution here is correct. It's correct. Good analysis here. And finally, my last question here for today is question 11. It says, which electron in sulfur is most shielded from nuclear charge? And then I have all of those questions here. So let me write this down here. It says, which electron in sulfur is most shielded from nuclear charge? And A says here, it says an electron in 1s orbital. B here says an electron in 2p orbital. C is electron in 3p. And then D is none of the above. Okay, so when we look at our electron configuration, let's draw this out, right? So we have sulfur here is going to be 1s2, 2s2, 2p6, 3s2, and finally 3p4, right? So let's draw out the electron configuration here. So sulfur is 1s2, and then 2s2, 2p6, 3s2, and 3p4, right? So I have these guys here, and it says which electron in sulfur is the most shielded from nuclear charge, right? So if you think about the shielding effect, if you were to draw out this, if I were to draw out the energy level diagram, I'll draw this out in red here. I'm gonna write basically 1s2 is here, then I have 2s2 is going to be here, 2p6 will be like so. This would be 3s2 is here, and then 3p and f4, right? So I have 1, 2, 3, and 4 here. So this here is going to be my electron configuration or energy level diagram for these guys here. If I want to talk about the shielding effect from nuclear charge here, you can think of the nucleus is somewhere down here, right? The nucleus of the sulfur atom is here, and then you can think of these guys as in terms of increasing energy level. 1s2 would be the lowest in terms of energy level, and then you have 2s2, 2p6, 3s2, and then 3p4, right? So it's asking us which electron sulfur is most shielded from nuclear nuclear charge. It's going to be my electrons that are furthest away, right? So in this case, it would be my 3p4 electrons here. They're most shielded because they experience the most shielding effect, right? The electrons here are very, very far away from my nucleus, right, in terms of distance. So it's going to experience the most, it's most shielded from nuclear charge here. So the interactions between the nucleus and the 3p4 electrons here are very, very minimal because of these electrons here. They're already bonded more tightly towards the nucleus. You can think of these as our valence electrons here. Experience the most will be the most shielded electrons because they are the outer parts of the atom here. So this solution is correct here. It says the correct option is C because it's 3p orbitals. So this solution here is correct. So these 3p orbitals are good. And it's saying that the outer electrons are repelled by the inner electrons, and thus shielded by inner electrons, right? Remember that these guys here are also, these are all negative charges, right? This is negative. These guys are all negative. So these guys are going to repel each other, whereas the nucleus here is positive, right? So these guys are going to repel each other, therefore it's shielded by most electrons here. So this solution is correct. Great analysis for this problem here. So I finished all my 11 problems here. I definitely took much faster than I did today, which is actually awesome here. Most of the questions were actually pretty simple that I could kind of go over and glance over and kind of solve on the spot, which is awesome. Again, feel free to tune in to my stream as well. Again, I stream from Monday to Friday. I teach math on Monday, Wednesdays, and Fridays. So tomorrow would be another math session with me as well, and chemistry on Tuesdays and Thursdays. If you have any questions, you can feel free to contact OneClass as well, or if you definitely tune into the live stream as well, you can also feel free to ask me there. Again, thank you so much for watching. You can find all these YouTube videos are going to be uploaded onto our YouTube channel as well, so you can kind of click play, fast forward, rewind, or pause in order for me if you missed something or if I went a little bit too fast in order for to kind of catch up on this material as well. If you want to kind of rewatch the videos, they're all posted there. So as always, thank you so much for watching. Stay healthy, stay safe, and have a great day. Take care.